Welcome back. Today we're going to talk about alpha carbon chemistry, and there is quite a number of topics that we have to touch upon. So this is a bit of a loaded topic, but I'll do my best to walk you through it. So the first thing we need to mention and talk about is the acidity of these alpha CHs. And specifically, an alpha CH is technically the carbon H hydrogen bond there is adjacent to a carbonyl, or at least to a highly electronegative group, such as the nitro group or the nitrile group. Now, what you probably already noticed is that in these circumstances, now obviously the first one that I'm listing here is the carboxylic acid. That is not a fair comparison because the hydrogen is directly bound to oxygen, and then there's other things that play a role in this hydrogen being so much more acidic. But the rest of them tend to be carbon hydrogen bonds. There's only one instance of a nitrogen hydrogen bond, but what you do notice is that the pKa's are relatively low for all of these carbon hydrogen bonds. Um, and the one that's spectacularly low is the nitromethane derivative shown here. It has a pKa of 9, and the reason for that is because the nitro group is so good at withdrawing electron density. You might remember that from the aromatic discussions we had in the past. So it's no different right here. So that pKa is substantially low. And when you continue going down the list, you'll notice that the second, or technically I guess the third acidic type of proton is the NH of an amide. We're looking at a pK of about 15, and it's not until we get to the aldehydes and the carbonyls, basically your ketones, your aldehydes, that we start then getting values of about 18, 19, roughly speaking. And the reason for that is that because now that you don't have that highly electronegative element or the presence of oxygen or nitrogen directly associated with this hydrogen, you have less incentive to withdraw electron density away. So this proton's a little bit more basic, but not by much. And by the time you get to an ester, um, due to the presence of the second oxygen that does dump electron density onto the carbonyl carbon, you raise the pK slightly more. And somewhat similarly for the nitrile, the pK is also about 25 because nitrogen is not as electronegative as oxygen, right? So you don't have as big an effect via induction, but it is still considerable. So, so don't get me wrong, it's still a considerable effect, but it's not as drastic as the nitro group, for instance. And then by the time we get to the amides, the alpha CHs are basically the least acidic out of the bunch. Also because of the same reasons as before, right? Namely that nitrogen is not as electronegative as oxygen, but because of that, it is more basic, right? So this nitrogen is dumping more electron density into the carbonyl, making this CH less acidic. Now, when you think about the traditional conjugate bases, right, of a pK table, like hydroxide or alkoxides or deprotonated amines, hydrides, and you start comparing these numbers, just to kind of remind you, right, when you compare an acid to a base, generally speaking, what you want to see is that the pKa of the conjugate acid of the base that you're going to be using, you want the pKa to be higher in value than the pKa of the acid itself that you will use for a reaction. That will ensure that the reaction goes to completion. So in other words, your carboxylic acids and your nitromethane, which have pKs below 10, are more than acidic enough to be deprotonated completely by hydroxide. Like that's strong enough of a base to do a full deprotonation to completion by all intents and purposes. If you instead were trying to deprotonate your amide, well, in that case, you will need to probably switch over to alkoxides to do a full deprotonation. Now, mind you, in that scenario, the pKs are very close to each other, so it might not be a full-on complete reaction, but it can still happen, right? Um, One thing that might prevent that deprotonation is, of course, the size of the alkoxide. The bigger the alkoxide, the more sterically encumbered the alkoxide is, the more difficult it's going to be for this deprotonation to happen. Now, the aldehydes and ketones that have a much higher pKa, you need a stronger base to deprotonate them. So at the very least, you will have to use a deprotonated alkyne to carry out that deprotonation of aldehydes and ketones. But truth be told, the alkynes are a little too small to effectively deprotonate the alpha carbon. More likely than not, they will attack the carbonyl carbon directly via a nucleophilic addition. So we rarely tend to use deprotonated alkynes for this. Instead, we kind of rely on the same thing that we do to deprotonate the alpha carbons or the alpha hydrogens of esters or nitriles or even amides, and that is to use deprotonated amine. That's a very efficient, strong base that can deprotonate pretty much all the different carbonyls. So the way you kind of ought to be looking at this is that, unless you're using nitromethane, for which hydroxide is more than enough to do the deprotonation, for your regular aldehydes, ketones, esters, nitriles, and amides, it is best if you stick to hydride or deprotonated amine. That's a strong enough base to deprotonate all these things to completion. And for full context, right, just to kind of highlight how drastically more acidic these CHs are, notice that, okay, if you compare it to regular alkane, it's basically like crazy, right? You have a pK of 50 for your regular alkane, whereas these things are more or less in the 20s, if not the teens, for the pK values. And if you compare it even to the most direct analogs, right? The fact that this CH is 3 steps away from the oxygen, right? So that the direct analog will be an allele fragment, or just basically allene, right? Uh, if you look at that CH still has a pK of 43. And what really makes the difference right here is the presence of oxygen. That high electronegativity and that polarization is what's allowing these pK values to drop down considerably compared to just your full-on regular hydrocarbons. So when you deprotonate these things, you gotta remember, right? You're deprotonating the most acidic proton. So for your carboxylic acid, you deprotonate that OH, you get your carboxylate. For nitromethane, you will be deprotonating that CH, making the carbanion. For the amides that do have NH bonds, you will be deprotonating that NH bond. That's the most acidic thing in that molecule, creating the deprotonated amide. And then for the other carbonyls, where you are deprotonating the alpha carbon, you simply end up making a carbanion in each of those positions. So the thing to basically keep in mind right here is that the reason, aside from polarization, that explains why these deprotonations are happening, to such an extent, is because you have a lot of resonance to help you out with that carbanion that's being formed. Basically, this lone pair that gets formed can attack the adjacent nitrogen, the electrons get kicked off over, and you form this resonance structure that has a full octet for all the elements involved, and the nitrogen now bears basically a double bond to the adjacent carbon, right? But all the oxygens are the elements with the most negative charge, right? So this is a much better situation than having the negative charge residing on carbon. But that full-on polarization is, the huge driving force for lowering the pK, to that extent. In a similar fashion, when you're looking at your aldehydes, right, the protonate that CH bond from the alpha carbon, a resonance structure in which the lone pair comes over to the carbonyl carbon and breaks that double bond explains why you tend to stabilize this. Now, granted, not to the huge extent that the nitro group does, but it does stabilize it somewhat. Enough that you're talking about pK of 17. And the same thing goes for ketones. The ketones, can have that lone pair attacking the carbonyl carbon, breaking the actual carbon oxygen double bond, right, and creating this fragment, which soon enough, I'll start calling it by its proper name. But notice that in both of the structures, you still have the polarization of the oxygen, pulling the electrons away from that carbon, right? Now, when it comes down to esters, you do have that effect as well, but because the adjacent oxygen has the option of actually attacking with its lone pair and rendering the carbonyl carbon less of a double bond, you have less of a tendency for these CH bond to be deprotonated and form the carbon ion, and that's reflected in the higher pKa in comparison, right? But nonetheless, once you form that anion, it can be stabilized via resonance, as shown right here. Okay, and then the last one will be the nitrile. Here, you basically stabilize this in a very similar fashion, except that because it's a triple bond, when the lone pair comes in to be stabilized via resonance, the electrons of that triple bond get kicked over to the nitrogen to form this this alene structure. Basically double bond right next to double bond. But that is the stabilization via resonance that this gets. It's not as great as the other ones, but it does the job nonetheless. All right, so let's talk a little bit then about the enthalpies of these reactions and to see, what's more favorable. Um, so one thing to kind of keep in mind is that, yes, you do have a resonance structure between the carbon ion and um, the oxo anion, right? Your alkoxide, if you will. This alkoxide derivative that is basically bound to an alkene has a term we refer to as an enolate. Enol because you have alkene and alcohol together, but you remove the proton of that alcohol, so now you call it enolate. 8 to emphasize that it's the anionic version, the conjugate base, if you will. All right, but that's the resonance structures. Now, technically speaking, the deprotonation and protonation events of the enolate are in equilibrium with each other. So you could actually, if you're looking at the carbon ion, yes, protonation of the carbon ion will give you the ketone back. Deprotonation of that carbonyl will give you back the enolate, or at least the carbon ion version of it. But if we strictly talk about the enolate, where you have the oxo anion and you protonate that, well, in this case you end up generating this neutral species, which is not exactly a ketone, but it's a direct derivative. And these two are technically in resonance with each other because of all, excuse me, not in resonance, they're in equilibrium with each other because of all the equilibria that's happening right here. So this one, where we do have the neutral species and the proton bound to oxygen, this is known as enol, because you have an alkene with an alcohol, bound together. So, we're basically going to see, to what extent is this truly happening, right? And I'm kind of already giving it away right here by showing that the arrow pointing towards the ketone is much, much more favored than the arrow pointing towards the enol phase. So, just to kind of highlight that, we could look at bond dissociation energies to get a sense of what's, what it would take to make this transformation happen. And what you have to consider here is, a number of bonds that are going to be broken and also form in this list that I compiled here on the right side of the equation. First of all, we will be breaking this CH bond here on the left side in order to form the enol. We would also be breaking the carbon-oxygen double bond, right, because we don't longer have that in there. And technically speaking, we have to break the carbon-carbon single bond because that goes from being single to double. So from the point of view of bond dissociation enthalpies, you have to break the whole thing if you're going to make any change to it. But those are the three bonds that need to be broken. Now, as far as bonds that need to be formed, well, we didn't have an OH before, so that will have to be formed. We didn't have the carbon-carbon double bond before, so that will need to be formed as well. And moreover, the carbon-oxygen single bond here wasn't there to begin with, so that will also need to be formed. So when you construct the enthalpy setup that way, all you have to do is now plug in the values, right? So we have the CH, the CO double bond, and the carbon-carbon single bond values depicted right here in that exact order, and you can compare them with the values here on the right side of the slide. And of course, you do the same thing with the products, right? The OH bond, this carbon-carbon double bond, the carbon-oxygen single bond. And when you carry out the math, you find out that this is actually an endothermic process. It would take more energy into the system, put into the system to transform the carbonyl into an enol. So the enol is not the preferred form. It's, up in energy, technically speaking. So it's not as favorable, but you still kind of have it. Now, in technical purposes, generally speaking, for regular ketones, regular aldehydes, you have less than 1% of that enol present, but it is still in equilibrium. So make no mistake, this happens, especially if you have some acid or base present in your, ketone or aldehyde, system. So with nitriles, we kind of have an interesting scenario here as well. Generally speaking, you're not going to have a lot of the enol derivative. And if you look at the bonds that need to be broken, right? So a CH bond needs to be broken right here. Carbon-carbon single bond needs to be broken. The carbon-nitrogen triple bond also needs to be broken, right? So those are the 3 bonds to be broken here. And the bonds that are being formed on the product are the carbon-carbon double bond, the carbon-nitrogen double bond, and the nitrogen-hydrogen single bond, right? So those are the bonds that are being formed. And when you enter all the values based on the table up here, what you find out is that this value is technically exothermic, and it is surprised me the first time I did this calculation. It is technically a thermodynamically favorable process, but you don't get much of this alene form because the activation energy is actually pretty high, and that's reflected in the high pKa. The fact that you have to use a much more aggressive base to deprotonate it means that, yeah, it's more difficult to form that carbon ion in the first place. But once you form it, yes, you get to this form relatively easily. Okay, so in the next video, I'm going to talk to you about the actual mechanisms of formation of the enol derivative, both in acidic and basic conditions. So I'll see you in the next video. Bye-bye.